Hey there, everybody. Welcome back. Today, we're going to take a look at 11.5 in calculus in the Anton book. This is on parametric equations of lines. So let's just jump right into it. We've always visualized lines as just being a line and points on it, but maybe for the sake of this argument, let's picture it as a road, and let's say a road. And I've got some vehicle starting at P0. And it drives to PT, and it takes time t to get there. So it's heading along this road right here. Now, it could keep driving in a straight line. It could take as long as it needs, but it's driving at a specific speed. Let's say its speed is locked. Speed is another way of saying speed in physics is velocity. Velocity is the same thing as speed, but it has direction. And so speed, like velocity, is a measure of distance over time, like miles per hour. Miles is a distance, hour is a time frame. So velocity is distance over time. So what's the distance it's doing here? Well, it starts at x0 and it goes to xt. And if we don't know what the initial value is, one way we can figure out what the distance for each component, x, y, and z, is to subtract the endpoint, or subtract the starting point from the endpoint. I could say this is x of t minus x naught, and we've got y of t minus y naught, and z of t minus z naught. Those are all components that are in the distance part right there. And we're not actually going to calculate the distance. I'm just doing each component separately, so I don't need the square root thing. I'm not going to do the overall distance. We're just going to do x by itself and y by itself and z by itself. Time, we usually use t. So let's use t for time. And the rate of speed, it might be going, it's got a fixed speed going along that path. But if I want to break it up into x, y, and z components, maybe we could give it a speed. Stupid phone. I could give it a speed of a, b, and c for the x, y, and z components. So we can kind of solve this for x and t. If I multiply t over, I've got t times, I'll put it back as v for a second. T times v equals, this is effectively point t minus 0.0. I'll write this up here. And if I add P0 to the other side, I get, and if I write in terms of PT, let's put PT on the left, I got PT equals P0 plus T times this V. So I could break this up into all of its X, Y, and Z components. So X of T equals X naught plus TA, y of t equals y naught plus TB, and z of t equals z naught plus TC. So it's how far we've gone. And I don't have a z component drawn on the page. I don't think, let's just say z is not really changing much here for the sakes of this picture, but every line is different. So we could describe this as motion along a line. Well, this line doesn't, it could be anywhere. I could have that, it's the same thing if I use the vector going from here to here. It's still doing that same thing. So it could be any vector. It's not just related to P0 and PT. Any vector that's parallel or any line that's parallel to a vector like this would follow the same mechanics. We just have a different P naught and PT. So this will work every time. And so this is another way of looking at how to do lines. You look at lines in terms of motion over time. And this is called parameterizing the lines with time. So these are called the parametric equations for the lines. And if I show this formula initially up here, PT minus P0, another way of writing that is the vector going from P naught to PT equals TV. Which equals T, A, B, and C. Okay. We're going to do a few examples of it, several examples of it. I thought I'd do some in this video just so it's not just boring equation generation. So let's take a look real quick at that. I want to bring this back down here. Maybe we'll flip that over. So find the line parallel to 5, -4, 8, and it's passing to the point -2, 4, and 0. And I'm going to put those equations back up over here just as a reminder. X of t is x naught plus TA, y of t equals y naught plus TB, and z of t equals z naught plus TC. So the line, find the line parallel of this vector, we could treat this as our velocity. The vector is going to be our velocity. And so this will be our P0 right here. So we're going to do, let's do each component one at a time. I've got x of t. I don't know where that's going to end up, but x naught will be its starting position, -2. And then we're going to add t times this vector, the x component of the vector, so 5t. And we'll do the same thing with the other ones, y of t and z of t. Y of t is the y naught component, is 4. And the z of t, the z naught component is 0. I don't even need to write it. Now we do TB. TB, this is B. B is -4. So we're going to go -4t. And Z is just going to be, that's C, so CT, 8t. So you can check it. If you plug in t equals 0, what happens? T equals 0. X of t becomes -2 because the 5t goes away. Y of t equals 4. And z of t equals 0 because all the t components are zeroed out. And we're left with P naught. We could generate later points on the line by doing t equals 1 and t equals 2. We'll do that in another example shortly. Next thing, I'll pause for a second, let you finish writing that or whatever. Let's take a look at doing another problem. Find the parametric equations for the line that passes through 2 points. P1 is 3, -7, and P2 is -2, -1. and then write them in slope-intercept form. Well, we already know how to do this the regular way. So maybe at the end, let's do the regular way. Let's do y equals nx plus b, the traditional algebraic way. That's where we're getting. So maybe let's do the parametric equations and then see what we can get to get there. For the parametric equations, we need a starting point and a vector. So right now we don't have a vector. And I could use either point as a starting point, but right now we don't have a vector. So let's make a vector. Let's just do P1 to P2. And remember, that is subtracting components. So P2 minus P1, the x component, -2 minus 3. And the y component is -1 minus -7. And I'm getting -5, 6 is my v. So I could do it two ways. Like, let's do each point. I could say x of t equals, let's use P1 for the first set. 3 is my x naught. Let me bring my equations back down so you can see them. 3 is my x naught, and a is going to be this component right here. The first component of my velocity vector, minus 5t. I could say y of t equals, what's my first component there? -7. And my vector is 6. So that's one way you could do it, or we could use the other points. -2 and -1 with the same velocity vector. Can I get the original points back from my parametric equations, either set? So we'll call this set A and we'll call this set B. Let's see what we need to do for set A first. Set A, if I set t equal to 0, I'm going to get that 3, -7, right? Gives me the 3, -7. And what by doing it, subtracting it one from the other, we're saying it's one time step. So let's try t equals 1. That would be one time step. T equals 1. I've got 3 minus 5 would be -2. And -7 plus 6 would be -1. So that gives me P2. So that's P1 and P2. Let's try it with the other set. If I plug in t equals 0 here, I get -2, -1, which is P2. Now I want to end up with -3 or +3. If you're not sure what time step it is, I'm sure it's kind of obvious here, but let's just work out what it would, how to figure it out in case you don't know. Plug in the x component that you're looking for. 3 equals -2 minus 5t. So I add the -2 over, +2, +2. My green pen is dying. 5, it shouldn't be, it's completely full. 5 equals -5t. And so t equals -1. If I do t equals -1, what do I get for the y component? -1 plus -6 is -7. And if I plug in t equals -1 for x, -2 minus 5 times -1 is a +5. -2 plus 5 is 3. So we get back P1. So it's just going backwards in time if we go start from there. Now, how can we get this, set this up so we get our original equations? Let's pick either pair of these. I don't know. The numbers are smaller for this set, -2 and -1. I like that a little bit better. So I'm going to use those two. Put a little line here showing that we're doing another step here. What I'm going to do is, this y of t has a t in it. I don't want t, I want x. So I'm going to solve this equation for t. So if I solve it for t, I add 2 to both sides. And then I can multiply by -1/5. And that should look like a subscript t right there. Now that I have t in terms of x rather than x in terms of t, I can take this and we can plug that in right there for that t right there. And what happens if we do that? I've got y of t equals -1 plus 6 times -1/5 times x of t plus 2. So let's just clean it up some. Y of t equals -1. 6 times -1/5 is -6/5. So -6/5, I'll distribute that. -6/5 x of t. And then -6/5 times 2 is -12/5. And if I rewrite this -1 as a 5/5, I'll do it at the end. I'll put -5/5 here. I can see that I get y equals -6/5 x minus 17/5. And we can optionally have the t component here, but we don't need it anymore. We've eliminated t. So don't really need it anymore. Would that be what we get doing it the traditional method? So doing y equals mx plus b, we need the slope. M is y2 minus y1 over x2 minus x1. It's probably been a while since you calculus students did a little bit of algebra. So y2, let's just figure out what this is. -1 minus 7. And x2 minus x1 is -2 minus 3. And this does give me a slope of -6/5. So then we have the good old y minus y naught equals m times x minus x naught. Also probably been a day or day and a half for you. Been a little while. We can plug in either point. I kind of like the -2, -1 again, just because it's got smaller values. Let's use that. So y minus y naught would be -1 equals, m was calculated at -6/5. X minus x naught is -2. So I got y plus 1 equals -6/5 x. These become a plus. I got the 2 again. 2 times 6/5 is -12/5. And if instead of doing 1/1, I do 5/5, I subtract -5/5 from both sides, what do we get? Y equals -6/5 x minus 17/5. So it matches. So the parametric equation of lines is, it might seem like it's more work now, but in 3D, working with parameterized lines actually can make stuff a lot easier. you've got things narrowed down to one component, a component in terms of time, rather than X, Y, and Z. That'll be it for this section. Peace.